Welcome back to another lecture. So in this lecture, I'm going to keep talking about how to determine whether a molecule is a polar or non-polar. So last time we went through linear geometry and also trigonal planar geometry. And after that one, we added lone pair to them, and we said what's going to be the hybridization and also whether they are polar or non-polar. And I hope you had the chance to watch those that video. So now I'm going to go through tetrahedral geometry, and we can have one lone pair, two lone pairs, or maybe three lone pairs and one sigma bond. Okay, so how about this? Let's go with AB4. Okay, we have four identical elements attached to the central atom, and one example is going to be CH4. Okay, silicon with tetrafluoride, carbon with 4 chlorides. Okay, you can use any of those. In this case, your central atom, for example, carbon, it will be attached to 2 hydrogen atoms. Okay, inside the plane. Okay, 1 hydrogen atom will be pointing to you. That hydrogen atom is pointing to us, so it will be out of the plane. And last one, it will be back of the plane. That H, I'm going to say it will be back of the plane. Now, if I connect them and connect them to the top atom, that's going to give me a pyramid. Okay, so I get a pyramid. And that's the reason, like in each pyramid, it has 4 faces, and that's the reason we call it tetrahedral. Okay, so I'm going to raise, I'm going to raise the line, and I will copy paste this one on the right side. Okay, so we have a pyramid, and that's the reason we call it tetrahedron. Let's assign sigma plus lone pair. We have 4 sigma bonds. Okay, so I'm going to say 4 sigma plus 0 lone pair. Before you add the sigma plus lone pair, be aware that if you don't have lone pair, electron geometry, and what's electron geometry? A geometry that's based on number of the pair around the central atom. We don't care about atom. This is 1, 2, 3, so I have 3 pairs. How many atoms I have? That's going to be the molecular geometry. Okay, so I have 4 pairs. Okay, it will be tetrahedral. And in this case, because we don't have a lone pair, electron geometry is going to be equal to the molecular geometry, and both of them will be equal to tetrahedral. How do I know it's tetrahedral? Because I got 4 pairs. Okay, I got 4 pairs. But anytime you don't have a lone pair, your electron geometry is going to be equal to the molecular geometry. Okay, so I have 4 pairs. Okay, because I have 4 pairs, or I have 4 sigma bonds, that means I have 8 electrons. I need to have 4 orbitals to accommodate them. And always you start with this: 1 from S, 3 from P, and 5 from D. Keep using those orbitals until you accommodate 8. You can put 2 electrons in each orbital. It doesn't matter what's orbital, because max, you can put 2 electrons in it. Okay, so I'm going to say I have 4 pairs. Let's use 1 from S and from P. How many do I need to use to make it to 4? I need to use 3 of them. So I'm going to say 3. And that's going to give me 1 plus 3. I get 4. Okay, how about orbital S and P? Okay, for S, always you will have 1. For P, okay, keep adding something to S until you get it 4. Until the answer for this addition is going to be equal to that 4. Okay, so keep adding to S from p orbital until you make it 4. Remember, the max number of p orbitals will be 3. You can't have 4 p orbitals. I wrote it on the top. Okay, so the hybridization, it will be sp3. Okay, now this is the geometry. Okay, what's going to be the bond angle? If you don't have a lone pair, bond angle, it will be 109. That's a perfect tetrahedral. Perfect tetrahedral will be 109.5. Okay, or how about this? Anytime you get hybridization of sp3, the expected theta is 109.5. Okay, why did I say expected? Because I want to know whether there is a lone pair or not. If there is a lone pair, you're going to drop something from 109. Okay, if you have 1 lone pair, go down by 2 degrees. If you have 2 lone pairs, then go down by 4 degrees. So you will subtract 4 from 109. So for the first one, it will be around 107. And this one, it will be around 105. Okay, cool. Now, is it polar or non-polar? Okay, anytime you have a perfect tetrahedral and you have 4 identical elements attached to the central atom, regardless of what you are using or writing, all that will be non-polar. Non-polar, doesn't matter. Why? Let's answer this. Okay, why it will be non-polar? Okay, so I'm going to raise those sigmas. Okay, let's add the blue hydrogen to each other. Okay, we have two forces. We're going to add them. The answer for them will be somewhere here. That's the force for hydrogen, the blue one plus another. Let's call this one 1, and that's 2. Okay, answer it will be there. Okay, and we're going to call this one 3, and this one will be 4. And the answer for them, it will be somewhere here. Okay. And this one, I'm going to call it F for hydrogen 3 plus hydrogen 4. Okay, I have 4 hydrogens. They are identical. In that case, you're going to say this force is identical to that force. And they are 180 degrees far from each other. So you're going to say this. Okay, you're going to say F for hydrogen 1 plus hydrogen 2 is equal to force of hydrogen number 3 plus hydrogen number 4. And because they are identical, when you add them, they will cross each other. They will cancel each other because they are identical. Or another way, because the bond angle between them is 180 degrees, those two forces will cancel each other. So anytime you have a tetrahedral and 4 identical elements are attached to the central atom, it will be nonpolar. Okay, nonpolar. Okay, question. What if I change one of the hydrogens? Or if I change 2 of them, or 3 of them? Okay, so if we change one of them. No, if you have 1, 2, or 3 non-identical elements attached to the central atom. In that case, all will be polar. Okay, all will be polar. Okay, let's write what I'm talking about. Okay, so let's say we have this. Okay, again, let's clean this one. Okay, I'm going to copy paste this one 4 times. Okay, okay, I need to shrink them. Okay, and copy paste this one. Okay, cool. So let's change one of the hydrogen. Okay, first one, nonpolar. Because all the forces will be canceled. This force will be canceled by that force. Call this one F1, that's F2. Now, what will happen if I change, for example, this hydrogen, I'm going to label one hydrogen and I will change it. I'm going to change the hydrogen. Okay, let's make the hydrogen fluorine or chlorine. Okay, it doesn't matter. So we're going to change this one to chlorine or fluorine. Again, so let's go with the fluorine. Okay, fluorine. So what do we have here? CH3 and 1F. That's going to be polar. Okay, why polar? Because this force is not identical. And why is not identical? Because here you have 2 hydrogens. Well, there you have hydrogen plus fluorine. Hydrogen plus fluorine. So they're not going to be identical. So say F1 and F2. Okay, I'm going to say F1 is not going to be equal to F2. Well, there, F1 was equal to F2. Okay, how about if we change 2 of them? Okay, remember, so we change this. We're going to change that one and the top one as well. So I'm going to change this and the top one. And both, I will say fluorine. Fluorine. In that case, I'm going to get one force here, another force there. Call this one F2, and that one is F1. Clearly, F1 is not equal to F2, and it will be polar again. What if I change 3 of them? Okay, that's the answer is going to be obvious and it's polar. So you can't cancel, the hydrogen by any force. So this force clearly is not equal to that force. Call this one F1. Should draw it there. So this force is not equal to that force. Call that one F1, and this is F2. F1 is not equal to F2. Again, it is polar. Okay, in all cases, polar. So if you have 4 identical elements, then it will be nonpolar. But if you change one of them, or 2 or 3 of them, for sure it will be polar. Okay, for sure it will be polar. So remember, we used to have 4 identical hydrogens. Okay, and I change one of the hydrogens. So let's say I'm going to change this, and I keep those yellow. No, I have 2 of them here. I change 2 of the hydrogens. Okay, and again, now I have 3 hydrogens, 3 fluorines, and this one is hydrogen. Okay, let me change the color about this one. So that's going to be a fluorine. Okay, one of you might say the third structure. So let's call this one 1, 2, 3, 4. Third structure. What will happen if you put one of the fluorine down? Okay. What will happen if you put one of fluorine down? Okay. So I want you to change your vision. Okay. When I say change your vision, so okay, the way you're going to look at it, the way I'm going to ask you to look at it, imagine you are looking to the molecule from here, either here or from here. It doesn't matter which side you are using. You're looking to it. So say we are looking from this side. What do I see? I see hydrogen and a fluorine. So I'm going to get this. I'm going to get carbon. Okay, carbon. I see a fluorine here and one hydrogen there. Then, okay, I'm going to see one fluorine maybe back. And hydrogen, it will be somewhere here. That's going to be hydrogen. Okay, so let's now add the forces. Okay, are they identical? Okay, it looks they are identical. Okay, it looks they are identical. Okay, it looks this is F for fluorine plus hydrogen, the F force for fluorine plus hydrogen. Okay, and they are identical, so they should cancel each other. Okay, they should cancel each other, and the molecule should be non-polar. Okay, non-polar. But what did I do? How did I move from this structure to that one? I just only changed my vision. Okay, changed my vision. I did not break any bond because I did not break any bond. So the molecule should be still polar. And when I say I changed my vision, this the way I looked at it. Okay, the way I looked at the molecule. Let's go with this. Okay, so purples are fluorine, or blue, any color that you see, they are fluorine. And yellow are hydrogens. I'm going to go with the green here because I have more green. Okay. So let's look at this. Okay. What do I see? I see that two greens are pointing to you. Okay, two greens are pointing to you. And where are the purples or blue? There are one here and one there. Okay, let's turn it that way. Turn it that way. Okay. So where is the vector for this to fluorine? It will be somewhere here. Okay, it will be somewhere there, correct? So it will be somewhere here. And where is the vector for hydrogens? For the hydrogen, it will be here. Okay, so this one is there. Okay, and hydrogens are here. So again, okay, give me. Okay, so the fluorines, you put it between them. And for the hydrogen, it will be right in the middle. Okay, so it will be right in the middle of them. Okay, clearly, fluorines will not be canceled by the hydrogen. Okay, fluorines will not be canceled by the hydrogen. Okay, now, I'm going to look at the molecule in a different way. I can look from here or there. Okay, in a way that's on one side I have two hydrogen, one fluorine and hydrogen, and another side again hydrogen and fluorine. Okay, but for now, do you call this molecule polar? Yes, because these two fluorines will not be canceled by two hydrogen. Only thing I'm going to do, I'm going to rotate the molecule. Okay, I'm going to rotate the molecule. I'm not really doing anything. It's just simply rotating the molecule in a way that you're going to see. Okay, you're going to see two here. Say one. One fluorine is pointing here, and that's hydrogen. Okay, where is the vector for them? Here. You might say this is going to be canceled by that one. Yes, it looks they are canceling each other. They are canceling each other. But I'm going to say, can you change your vision? Can you change your vision like you decide that technically you're looking? Can you change your position and look to the fluorine from one side in a way that two hydrogen will be other side? Yes, I can look at it from here. I see two fluorines and two hydrogen there. Or I can look. If I look from here, this area, I see hydrogen and fluorine. And then I see hydrogen and fluorine also here. Okay. So I'm telling you, because the only thing I did, I rotate the molecule. I didn't change anything. Okay. Molecule must be polar. And the left geometry is showing you that it's polar. So this one will be polar. Okay. Will be polar. Don't get confused. Okay. Don't get confused by the vector that I showed. Okay. It's a bit confusing. I get it. Okay. I get it. But if you can rotate, the molecule without, you don't have the right to disassemble any bond. Don't do it. Okay, you don't have that right. Okay, without breaking it. In that case, your molecule will be polar. Okay. Now, this video it has some embedded question. Okay, it has two of them, and this is the first question. Is asking what's the hybridization of the highlighted carbon, the one that I circled, and also determine whether the molecule is polar or non-polar. next subject that I'm going to go through it. Okay, now I'm going to introduce a lone pair. Okay, so I go AB3, E. Okay, now I have a lone pair. If you have a lone pair, you get the geometry like this. Okay, this is CH3 minus 1, and that one is NH3 minus 1. Okay, you have a lone pair. Lone pair is going to push down, and it's going to drop the bond angle from 109.5 by 2 degrees, and that's going to be 107.5. So in both cases, the bond angle is going to be around 107, okay, 107.5 or 107. Okay, now left side nitrogen has 0 formal charge, while here carbon, because it has 5 electrons around it. Okay, 5 electrons, so carbon, it has -1 formal charge. Okay, what's the hybridization? Sigma plus lone pair. I have 3 sigma and 1 lone pair. So the hybridization, okay, again, it will be sp, okay, sp3. Okay, hybridization, it will be sp3 because we have 4 pairs. Okay, we need to use 1. Okay, because we have 4 pairs, we're going to use 1 from S and 3 from P, and that's going to give us hybridization of sp3. Okay, remember, we're going to get 4 hybrid orbitals and the 4 hybrid orbitals of sp3. Okay, sp3. Is it polar or non-polar? Okay, is it polar or non-polar? So I'm going to write a note for you here. Note. Okay, if you have 1 lone pair, okay, if you have a lone pair, geometry, okay, that molecule for sure will be polar. Okay, 1 lone pair will be polar. Okay, how about 2 lone pairs? 2 lone pairs. It will be polar, except one geometry. Okay, except one geometry that it will be non-polar. Okay, so it will be polar under any condition except one geometry. And what's that geometry? Is square pyramidal. Okay, square pyramidal geometry. Okay, so square pyramid, square planar, my bad. Square planar. Okay, let me double check it. Or we can use xenon tetrafluoride, my bad. We can use xenon tetrafluoride. I think that's going to be a better example. Xenon tetrafluoride. Okay, because you have 2 lone pairs, those 2 lone pairs will cancel each other. So this molecule will be non-polar. Okay. Only in octahedral geometry, when you have 2 lone pairs are cross of each other, and the molecule will be non-polar. Okay, what will happen if I have 3 lone pairs? Okay, if you have 3 lone pairs, 3 lone pairs. If you have 3 lone pairs, your molecule will be polar, except, okay, your molecule will be polar, except this. You go, for example, Cl attached to iodide, forgive me, fluorine. Then say you have three lone pairs. Okay, that one, it will be non-polar, yes, non-polar. Okay, remember, if you change one of the fluorine to another atom, for sure your molecule will be polar, because I said if you have 1 or 2 or 3 non-identical elements, then you will have a polar molecule. But in this case, all the lone pairs are going to cancel each other, so your molecule will be non-polar. Let's review what we said. Okay, if we have 1 lone pair is enough to make the molecule polar, so you get a polar molecule. If you have 2 lone pairs, yes, your molecule will be polar, except when you are talking about square pyramidal. Square planar, forgive me, square planar. That one, it will be non-polar. Okay, how about the 3 lone pairs? 3 lone pairs, yes, it will be polar, except when you are dealing with linear geometry. Okay, now in this case, I have 2 sigmas, 2 sigma and 3 lone pairs, so 2 sigma plus 3 lone pairs. I get 5. So what's going to be the hybridization? That's a good test. You go 1 from S, 3 from P. So you use all the P orbital. You need something new, and that's going to be 1 from D. So the hybridization, it will be this. You get 5 orbital of S1, P3, and D2. Okay. Before I wrap this discussion, I'm going to show you the second question that you need to answer, and this is the second question. Okay. Find hybridization of oxygen and determine whether the molecule is polar or non-polar. In this case, we have two lone pairs. Okay, we have two lone pairs. You need to ask yourself: is it polar or non-polar? What's the hybridization of it? And also try to find the geometry, both electron and molecular geometry of this compound. Thank you very much. Now we'll see you soon.